is going to tell us a little bit now about her own Tom, but while she's trying to fix blue jeans, I'm going to take chair prerogative and say, well, Yair is checked now, and he says the SNEX code itself is only 75,000 lines of code, and the rest is like a wiki that never quite got off the ground, and there's some example code in there or something like that. So just to set the record straight, it's only 75,000 lines of code. Whereas the next one, what was it, 2,000? So I don't anyway. And then the other thing is, Lisa had asked me about what is an ORM because I had said that. So that's an object relational model. And so if we ever say anything that you haven't heard the term before, please ask. And so that's basically just turning a database record into a Python object. So if you had, a record that had a name, an address, and an ID or something like that in your database, this will just turn it into a Python object. And then it doesn't really care what the back-end version of SQL is that's working under the hood. It'll translate, the Django ORM will translate that Python object into your database, whatever your database is. So anyway, just wanted to say those two things. With that, I will give it to Rachel.
It is. So for the benefit of the people watching at home on Blue Jeans, I will fix the display screen. I'm sorry I can't do that while I'm simultaneously speaking. But this is the last talk, so I'll shut up after this. So I wanted this session to show you a couple of examples of the TOM Toolkit in use. So we are actually using it at LCO for a variety of different projects in different contexts. So I thought it would be interesting to illustrate. And the project I'd like to talk about is the microlensing project that is run by PI of Yanis Tsapras at the University of Heidelberg and the rest of our team. The goal of this particular key project is to characterize planets B on the snowline. You can see from this plot of mass versus orbital separation that Kepler especially and many other projects have done a very good job of filling in the planetary population at close separations. So now we're increasingly interested at exploring this larger region of planets further out. And the shaded areas indicate the sensitivity of different detection techniques. So we are using the technique of microlensing. This is sensitive to planets in the range of roughly 1 to 10 AU. And it's particularly of interest because its sensitivity is more or less independent of the planetary mass. It depends mostly upon the alignment of the source system in the middle here and an unrelated background source star. Because of that alignment, the rate of microlensing events is highest in rich star fields. And so we spend our entire time looking at the galactic bulge. Now, these are truly transient events. The events can last anywhere from days up to years. And the anomalies which betray the planet's presence in the system can happen at any time effectively, although the peak is most sensitive. And so this shaded plot on, whoops, no, wrong button. This shaded plot indicates the cadence that you need to observe at as a function of time throughout the event. And so you can see that because this is a transient event, we have to be highly dynamic to the behavior of every single target and schedule our observations accordingly. I won't go into the detail of methodology because that's really not the purpose of this talk, but the main goal of the project is to understand the characterization of the source star, which is key to understanding the physical properties of the lensing system. Now, most of our targets are rather faint for spectroscopy, so we do this by multiband photometry, which we use to infer the angular radius and the distance of the source, thereby breaking down degeneracies in the model. And so the Rome-RIA project consists of two different survey modes, both of which use the Sinistro images on the LCO 1-meter network. The Rome survey does a 3-color SDSS GRI survey of 20 fields in the galactic bulge region where we know from other surveys, such as OGLE, for example, that the microlensing rate is highest. And we monitor those fields using the Southern 1-meter network 24/7 for every 7 hours between the visibility period of April through to October for 3 years. We also take RIA or reactive observations at higher cadence for specific events of interest within those fields. And so the data products from this very long time-based survey are extremely long light curves, such as this one, with vary cadence from a wide range of different filters and telescopes, and also the in-depth color magnitude plots, as you can see on the right-hand side. So as far as the TOM Toolkit is concerned, the goal for this particular project is to build a database that will serve the data products from the end of this key project. Now, because we're coming up to the end of the project, we're actually not using it to observe anymore. So we had a TOM system running this project. So now what we're using it is to build a database that will serve the data products as an archive base. And you can see why we need a data archive for this. We have approximately 1.5 million stars. And so this is an interesting use case for the toolkit because it's a fairly large number of targets compared to what most TOM systems will have. It's also of order about 3 billion data points. So we're using this as a stress test for the package to see how well it behaves. It's also a slightly different use case in that because we're not taking our targets live from a broker or a catalog anymore, we're just ingesting these directly from another database. So we have a slightly different use case, which is another way to stress test the toolkit and develop it in different directions. So I have a few screenshots of the system that I will stress is under development. So as you can see, I've only ingested the data for one field so far. But I wanted to show you this as an example of what you can use. This is built with the toolkit, but you can adapt the toolkit for your own use. So you can see the way that I've changed the layout and the functionality because of the use case of the project. Each field is treated as a target object, and you can use some of the display tools to build interactive displays more or less straight out of the box using the existing templates that are in the toolkit source code. All I've done here is take one of those templates and adapt it for our own. This is one of our deep color reference images, and this is built using the Plotly library, so it's interactive, and you can zoom in, and I wasn't quite brave enough to do this as a live demo, sorry. But you can. I can run it on my laptop if you want to see it working later. So it is fully interactive, which is very nice through the browser. We have the other elements of our data products, such as the color magnitude diagram. And the use of these modern plotting tools is very nice because it allows you to mouse over any individual point and then identify where that data point is coming from in your data products, which target is producing that signal. It has some interesting search functions. We touched briefly, those of you who were here yesterday, we touched briefly on using Django forms. Here I've introduced just a couple of very quick examples of kind of search that all of us would like to do, such as searching by target name and also searching cone search, simple on position. So it has some basic search functions to explore the data. And it has the light curve data products. Again, these are interactive. And you can zoom into any data products and examine all of everything that you've produced from your pipeline. That's a really useful way of debugging the pipeline code that integrates with this. And you can see here that there's a whole bunch of other parameters. Now, we will cover this in some of the afternoon sessions later on. The toolkit provides a really easy way for you to add parameters to the toolkit. So it includes its basic astronomical parameters out of the box, but every individual science case has their own target-specific parameters. In these cases, these are some of ours, so you can see that the display is added there. You simply add these in the settings file, and you can set those to anything that you like. So the toolkit can easily adapt to any of your data products, your parameters. And so I'm going to wrap up there. Very simply, this was intended as a demonstration TOM. So the code is still in development, so be kind, but it is in a public repo, so feel free to take a look. And if you want to see how I did anything, then the example's there, and I'm happy to answer questions.
You mentioned a cone search. I'm just wondering how the TOM Toolkit handles spatial indexing on our index to do fast kind of positional cross-matching.
Austin, do you want to speak to that?
So out of the box, there is no spatial indexing, but if you use Postgres, you can enable it using PostGIS. They're pretty simple.
Yeah, they're called R-tree index. That's the name of the function. SQLite. That's right. Yeah, something you would customize in. Any other questions?
I had a small question. You showed here, and you mentioned here in other presentations, we've seen a lot of interactive plots and things. But I was surprised because you had one plot with like this mass of green points, and most of the at least the tools that I'm familiar with that are Python based for creating interactive plots don't scale very well to larger data sets. And I was just curious what you guys are using in the backend.
So we're using Plotly as our back-end engine. We've also used Bokeh in the past as well to great effect. And this project should be a good way to test how well they perform with large data sets. I've found that it kind of depends how you store the data products in the underlying database. So there are two different ways you can do that, and we'll cover that in detail later on this week. I've found, depending on the data product and the display that you want, you can make more or less wise choices as to how you store the data. So it really, the way it's handled within the toolkit, if you have a lot of data points that were taken at a single timestamp, then you can store those as a single list, and retrieving them is actually quite fast. But again, this is one area where we're deliberately stress testing the package to see how it behaves.
So we've seen for the Snacks 2 and now for this one, there's, okay, if you want to use any of these features, you can go into GitHub and see how they're written and adopt them, which is fantastic. I'm wondering if there's a plan to have for the TOM Toolkit, maybe it's a little soon for that, but like a gallery of examples of stuff that people have done.
Oh, that's cool.
Because if I wouldn't be here, I wouldn't know that you have this thing and to go look there. Whereas usually when there's something new that I'm trying to implement, and there's a gallery of examples, I didn't even know I wanted to do that feature, but now that I know it can be done and there's an example code, it's very useful.
That's a brilliant idea. Can you please add it to the ideas document in the shared folder I pointed out earlier? Thank you.
There's a page on the official documentation that lists all of the examples that we know of.
Yeah, so if you have examples, make sure we know about them so that we can put them on the page.
But thank you. Good idea.
Right. Well, let's move on and thank Rachel again. So our next speakers are Matt Daly and Lindy Lindstrom, and they are going to tell us about a slightly different use case for a TOM, and they're going to talk about using this to schedule calibrations on the Las Cumbres Observatory network.
Okay, great. So I'm Lindy Lindstrom, this is Matt, and we are two members of the software team at Las Cumbres Observatory with Austin and David and Curtis and Brody and John and Elizabeth, so people you may have interacted with. The purpose of this talk is to perhaps broaden your idea about what a TOM can be and what the TOM Toolkit is capable of. Thank you. Right, so we're using a TOM to, and this is a pilot project, to do calibrations. So our job is to support the, scientists, internal scientists, operational scientists, and instrumentation scientists at LCO. Part of that job is to schedule calibrations throughout the night, which feed into the reduction pipeline and make your science images. the code we have for that
Right there. Yeah.
is called calibration utils. And right, it's calibration utils schedules calibrations on a global network of robotic telescopes daily. The problem that we have is that maybe like SNEX, but this code, calibration utils, it's a legacy code base that is, it's seen a lot of owners over the years, and probably seen software like this. It's large, it's complex, it's repetitive. We're interested in efficiency, so it's time-consuming to maintain, and it's central to the science of LCO, no reductions without calibrations. And one of the other problems that we're trying to solve is that the code and the configuration are tightly linked. If an operations scientist wants to change the number of biases on any given night, well, that could involve them making a code change, making a pull request to us approving it, then redeploying calibration utils, and that's an inefficient process for a configuration change. We'd like to separate those out. Why am I going the wrong way? Okay, there we go. So one of the ideas that we had, and it was kind of a naive idea of mine when I was thinking about our spectroscopic standards. You know, we have a set of targets that change throughout the seasons of the year. They need to be observed on a daily cadence, and well, targets, observations on a cadence, maybe a target observation manager might help us with that. And so we thought, oh, that might be a potential application for the TOM Toolkit. So again, our goals separate the operational and development aspects. We want to get the configuration out of the code. So Matt and I can worry about the code. Our operations scientists can worry about the configuration, what happens when. And also, in addition to that, right now our code is a bunch of Python scripts triggered by cron jobs. You know, if we're really interested in what's happening, we look at log files. That's fine for us, but our operations scientists we'd love to give them a web-based GUI utility where they can really configure things and look at the results. So, yeah, that's maybe not what you guys think of as a TOM, but that was a novel application, and that's why Rachel asked us to sort of go into this. So I'll hand it off to Matt. He'll talk about some details.
Yeah, so the TOM worked pretty well for us, and I want to highlight a few features that we utilized that came in handy and that you might find useful as well. So we've heard a lot about targets, and one of the core features of the TOM Toolkit is target list management. And in particular, Rachel touched on this, adding arbitrary extra fields or metadata to those targets. In addition to that, there are a number of facilities that we've and outside collaborators have created interfaces for to submit observation requests. In our case, we're submitting observation requests to our own facility, so we're using the LCO facility support. And that provides us not just construction of the JSON request, which itself can be a little bit daunting if you don't have a nice tool for it, but also submitting and validating the observation to make sure that everything goes, or everything is valid. In addition to that, Lindy talked about the support for the operations and instrumentation scientists. There's a web-based GUI. There's user management and authentication. We only want certain internal users to be able to change parameters. And there exists some TOM Toolkit features that we did not use. We did not use the alert functionality because we already have a set of standard targets. We're not ingesting alerts or working with alerts at all. So I just want to quickly go through kind of our development workflow and talk about how did we get to where we were? How did we start trying to get feature parity or start trying to schedule calibrations using the TOM? So we started with a set of targets that we already had defined in the calibration utils project. These are photometric or spectroscopic standards, along with some extra fields. And these are those target extra fields that Rachel talked about. These extra fields for us defined seasonal start and end dates for a given site. So at a given site, we're able to define the name of the site, seasonal start, which is a date time, and seasonal end, which is a date time. when we want to observe during the year a given target. And you can see that in the target detail page, these are automatically populated when we create the target. So from there, we have a list of targets. We'd like to filter it down. We have a site. We know which site we want to schedule the standard at. And we know what day today is. So we want to schedule a target whose seasonal start date is before now and whose seasonal end date is after now. Pretty simple. And we've heard some discussion about the Django ORM, and I just want to, this is a block of code, and it looks kind of scary at first, but this is the power of the Django ORM. I have a set of targets in my database, and I'm able to query the database and filter on 3 components. The site, so I want to be able to get a target that is associated with some LCO site. I want to say that the seasonal start date of the target must be less than or equal to now, and I want the seasonal end date to be greater than or equal to now, and that gives me a target that I'm going to schedule a standard for. Finally, I wanted to go ahead and change the LCO observation form to be able to modify my observation to add additional configurations. So what that means is in the standard LCO observation form that we use to construct the request to LCO, there's only one type, it only has support for one configuration out of the box. But we were able to go ahead and extend that function and define 4 configurations for our observation. We take 2 spectra, a lamp flat, and an arc. And that was really natural for us because we took what worked in that observation form, but then we were able to extend it and build on the functionality that was already there. Finally, we were able to feed our chosen target into the form we created and let the TOM Toolkit construct, validate, and submit our request to our observation portal. That, hand it off to Lindy.
So just to wrap it up, so think broadly about what a TOM can be. We're encouraging you to be creative as you think about how to apply the TOM Toolkit. We came up with this idea, and it was surprising to the authors of the TOM Toolkit, which is the mark of a successful software project when it's used for things that you don't anticipate. In our development, and this is we've only worked on this for a short time, and it's a pilot project to see if this is working. But we looked at the source code, and these are things that you'll do throughout this week. So don't hesitate to do that. We were lucky enough to have resources readily available, but they're readily available to you, although not in the same building. So ask questions, make requests of those guys, and also make contributions. For example, you saw it maybe in SNEX 2. Jamie had changed the navigation bar. We wanted to do that too. There's add a calibrations element to the navigation bar, but I felt like that was a little awkwardly done. So I made my own change to the TOM base code, made a pull request to those guys, and they incorporated that into TOM base. So you're all encouraged to do that. The work in progress calibration TOM is available on GitHub, and you're welcome to take a look at that for how we solved certain problems.
We have time for 1 or 2 quick questions.
My job to be the workshop glossary. What's a JSON request?
JSON is a way of taking and packaging data. I should have touched on that. So the way LCO works is that somebody submits a request over the internet using JSON as to encode all the information for that request. The window of the observation, the maximum air mass, those sorts of things. So that's all encoded in JSON.
I haven't dug into the code myself yet, so maybe I just don't know how this works. But I noticed you added those extra keys of seasonal start and seasonal end. But the way the code that you showed was like you had to give the name of the key and then the value of the key rather than just like key equals value like you normally would do, I think, in an ORM. Can you explain how that works a little bit? Or maybe I'll learn tomorrow. I don't know.
You will learn that during the week.
Okay.
And right, so that particular bit of code was not an assignment. That was a query into the database. Give me the records for which this key has that value.
But for example, if I wanted to query on right ascension or something, wouldn't it just be right ascension equals X?
Because they're dynamic fields.
Okay. Okay, yeah.
Right.
So those are dynamically added. Also, if you want to.
Okay, that answers my question. Thanks.
So we heard from Jamie and Curtis earlier that the SNEX 2.0 doesn't yet have the cadenced observation. One thing we have in SNEX is observe this every 3 days and make sure it gets done, and if it doesn't, re-request automatically. I'd imagine for calibrations, you'd need something similar of just get this every day or something. Is that functionality now a part of your TOM or the base one? Or?
The way we're working that is, another thing that you'll see this week is how to create a management command, a Django management command. And those are basically Python commands that can trigger events in your TOM. And so at a certain level, we could run a cron job that would trigger the TOM to do that. So as basically a cron-based endpoint to create the cadence that way.
All right, so let's thank our speakers again. All right, and so we're going to change gears a little bit to more of a discussion-based section. In just a moment, I have like 2 slides. Good. Good. All right, so my slides did not show up here, Rachel. They're split. Yeah, they were. They're in the TOM workshop presentation. Yeah, let me see. That's a good point. Technical difficulty slide right now. Hey, there we go. So I think everybody understands the 600-pound gorilla, but probably also the 200-pound gorilla in the room, being ZTF and LSST that are coming up. And, ZTF is going now. And so we're really to the point where surveys are beginning to kind of overwhelm our follow-up capabilities as a field, as a whole community. And so we wanted to kind of go from this guy where we're drinking from a fire hose of targets down to something a little bit more manageable. So the idea is we want to have some discussion on what do we need in, say, the TOM Toolkit, what do we need in terms of facility communication, things like that, to really make the science happen. So we can go lock ourselves up, write code, but it doesn't do anyone any good if it's not actually useful for us doing science, right? And so these are some of the things I've written down. I'd love to hear more discussion. So I have things like, how do we get targets from surveys? Can we directly hook into survey data streams like ZTF? What are the role, so do we have to go through brokers? Probably have to go through brokers. How do we choose prioritize targets alerts? This gets into some of the things Antares works on. Is that something that needs to happen in the TOM Toolkit? What can we do to make that easier? And as these large surveys happen, how do we make sure we try to limit our selection biases? How do we interface with observing resources? Can there be something like a Keck API where you just click a button and Keck could observe? That seems magical. Monsi says no. Monsi's decided that's not going to happen. How do we coordinate follow-up resources, right? I don't need to use an 8-meter telescope on a 16th mag supernova at the moment, typically, but that's not how we've operated traditionally. How do we get access to consistent data products in a timely way, in some kind of automated way as well, without necessarily a human standing in the way and slowing down the data flow? And really, kind of at the heart of this, what are the tools that we need for TOMs and even other tools outside of the TOM Toolkit to make this work? And so I think we're going to have a discussion section, and we're going to go to the breakout rooms. Once you get to the breakout room, we're going to nominate us. You will nominate a spokesperson, and then we'll come back in a few minutes, or a few minutes before lunch, and we'll hear reports from the spokespeople. Are there any other topics of discussion that people want to have on the table before we go? No. These are possible topics that I think bear some discussion. We can then try to break them apart into different rooms in just a minute. Done silence? Sure. So I don't think intrinsically, I think we rely on the brokers to do that, and we rely on the broker APIs to do that. Is that right, Austin? That's right. Absolutely.
That's whatever plugin.
Okay, we have some feedback from the Blue Jeans channel, so I will try and relay what they're saying. So from Sri Kulkarni, the P6C SEDM is now an intelligent telescope. You can send objects directly to the telescope and can have a pool of targets for routine observations. And he says they are planning to build the same feature to KP84, which is fully roboticized, and mentions that the key for astronomers to dedicate their 2-meter telescopes for a single cause. This requires that they modernize telescopes and build a quality and unique instrument. I will keep trying to relay online chats as they go.
So, I mean, we're already in the era of more targets than we can follow up. Well, yes. But hopefully with better classification, with machine learning, we won't be able to get measurements of everything we want. Now, what I'm interested in is the real-time kind of priority changing of your target list. Hopefully you'll have a target list that's much larger than could ever be followed up, but we get the best observations at the best times for your specific kind of thing. But also, as soon as you introduce real-time systems like that, or quick backwards and forwards, we need to avoid kind of gaming of the system. So robotic telescopes at the moment, there's a little bit of gaming of the scheduler you can do, but because it's clunky, it's kind of, quite a manual process to enter 5 observations with different constraints, and then as soon as it's done, cancel 4 of them. How do we stop the kind of the gaming of the schedulers in that kind of era. That's what I'd be interested in.
Can you pass that down to you?
So other than interfacing with surveys and brokers, I think another important interface is with catalogs. If you happen to be in, I'm looking for things in these types of galaxies or in this position in a galaxy or any kind of contextual information. So I know that's built into some of the brokers, but is that the idea, or can the TOM Toolkit also talk to catalogs of galaxies or various types of catalogs for contextual information?
How does the TOM Toolkit now handle sort of annotations? So, there were some various examples of people sort of looking at data and then sort of looking at, but you want to be able to annotate that and then use those annotations to make decisions on priority or, selection and so forth. So I'm interested in knowing that, or if that needs to be developed.
Annotations? Okay, yeah.
Also, a direct question and maybe a point of discussion. Does TOMS currently have the ability to interface with the various VO systems that are out there, either the one in Europe or CADC or IPAC or whatever else?
We have VO support. We have some VO support, but I don't think it's... We've done a little bit of VO, but we haven't done a lot. Is that right? I don't have time for that discussion right now. So it looks like there's kind of a few different things. So we have, kind of a brokers and how do we get targets question. How do you filter targets kind of group. We have observational facilities with, something about data. And then something more based on just like direct questions about the TOM usability, so VO event, asking about how to do this annotations, things like that. So I think that those are three natural groups. So let's put some of the interfacing with surveys in, let's see, Rachel, which rooms do you want to put these in? So sure. So if you're interested in doing like alerts and getting things from brokers and getting targets, okay. That looks pretty big. Main conference room. All right. No, the main conference is that the library or is that the other one? Oh yeah. Yeah, it's just the one directly outside. And then what about the coordinating follow-up resources with across observatory resources? Okay, great. Let's do that one in the library, I guess. And then just any other TOM tools, just kind of general tools for doing science. All right, that looks like that'll fit nicely in the garden conference room. All right, so once you get there, nominate a spokesperson, and we will be back at, what time is it at? We will be back at 12:15. Oh.
Sorry to gate crash at this point of view, but there's been a slight change of plans because of something I didn't know about when I came up with the schedule. And that is that Mount Wilson will be turning on the display at 12 noon sharp. So if you want to see that in the car park, be in the car park at 12 noon, and we'll also do a group photo while we're at it. And then we'll go into the discussion session, and maybe we'll push a little bit more into lunch at the time.
Okay, so what time do you want them back here?
Sorry?
Yeah, so they're going to...
Apparently it's well worth seeing.
All right, so parking lot at noon, and then what time do you want them back, 12:30?
Yeah.
And then back in here with a short wrap-up summary is at 12:30, and then we'll go to lunch.